So reaction mechanisms is going more into detail about the collisions that have to occur for a reaction to take place. So we're going to look at those collisions in a more direct way. So what a reaction mechanism is, well, what's not. When we look at a chemical reaction, let's just pick some reaction. Let's say we have 2H2 plus O2 going to 2H2O. We know that collisions have got to occur. We have hydrogen and oxygen somehow needing to collide and in the process making water. Now, this is not a really good depiction of what's happening on the molecular level. It's not that two of these and one of these happen to be need to be on a collision path and all three of them have to hit in one little spot and run into each other and out pops this. That is typically what does not happen. Instead, what we have is a sum of these things called elementary steps. Elementary steps are a series of simple reactions where this collides with this first. It makes this. And then this collides with this to make this. And when it's all said and done, we finally end up with the product. So what is an elementary step? Let's get the written definition. A series of simple reactions that represent the progress of the overall reaction on the molecular level. Okay? Those collisions and what collides with what. The mechanism is just the series of these elementary steps. So that's what a reaction mechanism is. It's the series of elementary steps that together make up the overall reaction. So let's look at one. Let's look at this reaction. Not the one I've written up here, but a kind of a similar deal. We have two NOs reacting with O2 to make two NO2. Now, let's say they're all gases and they're running around banging into each other. While monitoring, now this is what they observe. Remember, we start with an observation. We see things happening on our level, and then we try to interpret what's happening down there on the molecular level. When we're monitoring this reaction, we found that for a brief instance during the course of this reaction, N2O2 forms. So it's there for a little bit and then it goes away. Well, in the reaction, there's no N2O2, so something has to be happening on the molecular level where that's being generated and then gets used up. Okay, so here's a proposal. Okay, what this means is down there, which is what I just said, on that molecular level, two molecules are not colliding with one O2 and boom, you've got two molecules of NO2. That's not what's happening. Somehow, you've got some more things going on. It's not a one-step process. So here's the proposal. What if this happened instead? You took the NOs, okay, remember the overall reaction, okay, it was 2NO plus O2 giving me 2NO2. So let's say that these two collide first. Now when they collide, in step one there, they make the N2O2. And that exists for a brief minute, and then brief fraction of a minute, who knows how long, but it occurs that it produced there. Then that N2O2 collides with an O2 molecule, and then you end up finally forming the products of the reaction. The N2O2 is no longer there because it got used up in the second step of this mechanism. All right, so this would be the elementary steps. We have elementary step 1 and elementary step 2. If it's a good mechanism, then these elementary steps have got to add up to the overall reaction. So we see that N2O2 is occurring on both sides of the equation. It's being produced in step 1 and then consumed in elementary step number 2. Since they occur on opposite sides of the equations, we can cancel them out. They're called intermediates. If something appears in the mechanism early and then gets consumed later in the mechanism, then that is an intermediate, and it does not show up in the overall reaction. So we cancel them out, and what do we have left? Well, we have those two NOs coming down, okay? Our overall reaction that we were wanting. The two NOs are there, the O2 is there, and you formed two NO2s. So when you have a good mechanism, their elementary steps add up to the overall reaction that you were looking for. And your mechanism gives credence to what you observed. So in this case, we observed the N2O2. The mechanism shows a possibility of how you could have formed N2O2 in the course of the reaction by the collisions. Okay, now there's some terms that go along with these mechanisms, just like we had terms that went along with orders and rates, you know, those rate laws. Unimolecular is an elementary step that involves only one molecule. Now this is not really that common, but if you have a molecule and it doesn't have to collide into anything, maybe it just gets a lot of heat energy and the molecules just fly apart, okay? That would be where you only have one reactant particle. Bimolecular is by far and away the most common elementary step. One molecule collides with another molecule. Two molecules in the collision. Okay, they might be the same molecules, they might be different molecules. Termolecular means three molecules are colliding into one spot. These are rare. Okay, there are some reaction mechanisms that require this to be part of the mechanism, that you have to have these, and there's evidence that gives rise to that, but that would be a slow step because three molecules buzzing about in the world, okay, in your reaction chamber, that are all just randomly running around, to have those three molecules collide in the exact space and time simultaneously won't happen as often as just two molecules colliding. So they tend to be slower steps if they rely on a termolecular reaction. So if we look back at this mechanism that we had before, okay, what type of elementary step does it have? Okay, I have two elementary steps. They are both the same classification. How would you classify them? Well, they're both bimolecular, okay? They don't have to be different. The first elementary step there, an NO has to collide with an NO. Okay? They could have written it as two NO, but they don't in elementary steps. They show them as individuals because they have to collide with each other. Okay, now this is something that blows people's minds at first. We know that when we did overall reactions, you didn't use the coefficients. But when you get into rate laws, mechanisms, and you look at elementary steps, you absolutely can use the coefficients as the orders of those elementary steps, okay? It has to do with collision theory, okay? This one-to-one relationship between a collision and formation of a molecule. So you get to use the coefficients. So if this were an elementary step, only if it was an elementary step, we could use the fact that there is a one coefficient and make it a first order in A. If this were an elementary step in a mechanism, its rate law would look like this. If this were an elementary step in a mechanism, its rate law would have a square because you have two of those A's, and that's 2A, 2 coefficient becomes a 2 power. Okay? Please remember, when you go back and start studying for the exams, you cannot use those coefficients for an overall reaction. When you know an overall reaction, you cannot use those powers, those coefficients as the powers. They have to be experimentally determined. But when you know a rate law has a bunch of elementary steps, and each one of these elementary steps you can use the coefficients as the orders. Okay? So that's a reminder. How do you determine the order of an overall reaction? The answer starts with an E. Experimentally. Now, when you have a series of reactions, one of those steps is going to be the slowest step, and we call this the rate determining step. The slowest step in a sequence of steps leading to product formation. When you know the slow step is what determines the rate of the overall reaction. So, if you're on a production line, there's all of these steps that have to take place. It can only come off the end of the assembly line as fast as the slowest step. So somebody gets really, really slow and does their step really slowly. The next person in line is just standing there waiting for that to happen. And he can't go any faster because he's waiting for the slow step to take place. Okay? If the step before it is going really, 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 really fast, it's just piling up there. It's not going to come off the assembly line any faster than the slow person who's doing his step really, really slow. Whatever is the slowest step determines how fast it will come off of the assembly line. If you think of your reaction as the assembly line of elementary steps, this elementary step has to happen, then this elementary step has to happen, and then this elementary step has to happen. The slowest one determines how fast the reaction is going to take place. We're going to look at a specific example of this with a demonstration with me making booklets, okay? So we'll insert that here.
We're going to simulate a mechanism and talk about a rate determining step through the simulation of this mechanism. It's going to have 3 steps. Our final product is going to be a little booklet. So we're going to staple this booklet together. The booklet's made of an orange sheet and a blue sheet. There's going to be 3 steps to this mechanism. One person is going to collate the sheets together. One person, that's going to be me, is going to fold them into 3 parts and hand it off to the next person who's going to staple the booklet to give us this final product. So what we just demonstrated was a process that represents a chemical reaction taking place. And it's representing a three-step mechanism. We have the collating of the pages, we have the folding of the pages, and we have the stapling of the pages. And if we're going to look at the overall rate of the reaction, we don't look at from beginning to the end and say, how long did that take? We look at it coming off the assembly line and say, how many can we produce in a certain amount of time, and monitor that. So that's what you first need to realize about rates. It's not start to finish, but coming off the assembly line. So we produced 6 booklets in 45 seconds. So if we were to find the rate, we'd do 6 divided by 45, and that would be booklets per second. And now we want to think about what is the rate determining step of that process. We have the process of collating, putting the 2 pieces of paper together. And if we sped up that process, it wouldn't come off the assembly line any faster. And we had the stapling end of the process, which, you know, if he could staple just really, really lightning fast and staple as fast as he could, it still wouldn't come off the assembly line any faster. But my step, which is to meticulously fold it in a tri-fold, put them together and toggle them and fold it, that was a slow step. Now, if I could figure out a way to do my step faster, that would speed up the overall process. So we'd call this the rate determining step.
All right, let's look at this mechanism. Rate law of this reaction, we have an overall reaction. The rate law was determined to be this, and it was determined experimentally. Okay? This mechanism was suggested for it. The question that I have for you is this: which step would have to be the rate determining step? Well, what we'll do is we'll go through and we'll write the rate laws for each of those steps. So, step 1. We look at the elementary step number 1. The rate law would look like this. Rate is equal to, and I'm going to call it 1 for the first step, and I'm going to call this K1 for the first rate constant. It's going to be H2O2, okay, to the first power, and I minus to the first power. I use the coefficients to be the powers. Step 2. All right, bear with me while I get me another pen. I'm wearing out the pens today. I like this one. Okay, so step 2. Ah, look at that, right. Okay, step 2, rate for the second reaction is its rate constant, so I'll put a little 2 there, times OH minus times H plus. Step 3, rate 3 is equal to K3, and then we look at those substances. HOI to the first power, and H plus to the first power, and then I minus to the first power. Okay, so those are our three rate laws for our three elementary steps. Now, which one of these matches what was experimentally determined as the rate law? Well, that would be this one, right? That one exactly matches the overall rate law with H2O2 to the first power and I minus, there's a minus there, to the first power. So that tells me that this must be the rate determining step. Sometimes it's called the rate limiting step, but it determines how fast this reaction can go. It can only go as fast as that slowest step. So it's plugging away, and as soon as this happens, this happens, this happens. As soon as this happens, and this happens, this happens. Both of those very rapidly, but it's not going to come off the assembly line, and the overall reaction is not going to be any faster than that slow step right there. So we can label it as the slow step, okay, and that's what they often will do. What is HOI? Okay, what is that substance right there? Well, it forms in one step and is consumed in a later step. So those are your going to be able to be canceled out. The OH minus is formed in step 1 and consumed in step 2. So they are going to be able to be canceled out. What are they? Okay, which one of those things are intermediates in the mechanism? Well, it would be both those things, the things that are formed and then consumed. All right, so it would be D, formed and then consumed, and we could cancel them out to give you the overall reaction. Now, this one is a little bit different. Sometimes you have a mechanism in which the slow step has intermediates in it, and you never want to leave it with the intermediates in it. And so I want to show you how you can come up with the overall reaction, the rate law, when you know the slow step. Now here I knew the slow step, or actually I determined this was a slow step, but let's say I knew this was a slow step, I would know this was the overall rate law. They go hand in hand. The rate law of the slow step is the rate law for the overall reaction. I know that the second step of this is my slow step, and if I were to write the rate law of this reaction, okay, rate law of that second reaction, okay, I would have O3 raised to the first power, and I would have O. O is not a reactant. Look at my overall reaction. It is an intermediate, and we never want to leave an intermediate in our rate law. So we go to step 1, which is equilibrium. Okay, it's an equilibrium, and it has a forward reaction and it has a reverse reaction associated with it. And I'm going to write the rate law for the forward and reverse reaction down above this here. Okay, for the forward reaction, the rate, and I'm going to call it F for the forward reaction with a 1 because I'm talking about the first reaction, would be equal to the K of that forward reaction times its reactant, which is O3. Okay, and it's raised to the first power. For the reverse reaction, the rate of the reverse reaction of this reaction 1 is the rate constant of this reverse reaction, and if it's going reverse in that direction, then the O2 and the O are my reactants. So I'm going to write O2 and O. Okay, now I have the forward reaction and the reverse reaction. I have the rate law for them. At equilibrium, by definition, the rate of the forward reaction and the rate of the reverse reaction have to be equal to each other. So I want to set these two things equal to each other. Okay, I'm going to do this down below. The rate, the K of the forward reaction, and I really don't like the way that looks, so let me see what I can do here. Okay, the K of the forward times O3 is equal to the K of the reverse times O2 times O. And what I'm trying to do is get rid of this O. That's my whole goal here. So now I've got another equation that has an O in it, and this O, if I solve for it, looks like this. O is equal to KFO3 divided by KRO2. I have taken these over to this side. I can substitute in this O with all of this information into this equation. I'm trying to get rid of that O right there. So the rate of this second reaction is equal to K times O3 that I already had. I didn't change that. And in place of this O, I'm going to do all of this. KF over KR, O3 over O2. Now, a constant times a constant times a constant is a constant. So rate is equal to a constant, and then I have these O3s, they're squared, and I have an O2 in the denominator. That's a -1 power, okay? So now this is the rate law for the reaction based upon the slow step, but substituting out this intermediate for non-intermediates. Only time we're going to ask you to do something like this is when the slow step, look at the monitor, look at the PowerPoint, when the slow step has an intermediate in it, you can replace the intermediate. We'll always give you an equilibrium before it that's fast, where you can do a similar type of substitution. So make sure you note what I'm doing here and why I'm doing it so that you could do this in the future. Okay, so what's up next? Sometimes we need to speed up a reaction, and we can't raise the temperature. We can't do the concentration more. We want to speed it up in another way. We're going to see what that other way is in our next lesson.